Educational Module, Statistics for Data Science, Learning Unit, Core, Probability Functions supported in R. The probability distribution depicts how the values of a random variable are distributed. For example, if we examine the outcome of successive coin tossing, we see that they followed a binomial distribution. Or, if we study the means of a sufficiently large number of samples of a data population, they will resemble the normal distribution. Since the characteristics of these theoretical distributions are well understood, they can be used to make statistical inferences on the entire data population. As we already mentioned, data sets are composed of two main types of data: numerical like integers, or floats, and categorical like names, or lactops brands. Numerical data can additionally be divided into two categories: discrete and continued. Discrete data can take only certain values like the number of students in a school, while continuous data can take any real or fractional value like heights or weights. From discrete random variables, it is possible to calculate probability mass functions, while from continuous random variables we can derive probability density functions. There are many different probability distributions in nature, as depicted in this figure. In this unit we will be discussing some representative distributions that are typically used for data science tasks. R offers a variety of built-in functions associated with probability distributions. In this unit we will discuss some basic probability functions in R. Functions for different distributions are very similar, and you can always resort to R documentation for the specifics. To get a full list of the distributions available in R, you can use the help command, passing the word distributions as argument. Some of the most popular statistical distributions supported in R include the normal and the log normal distributions, the uniform distribution, the exponential distribution, the Poisson distribution, the binomial distribution, the F distribution, the logistic distribution, and the chi-square distribution. For every distribution there are 4 commands. The commands for each distribution are prepended with a letter to indicate the functionality. D returns the height of the probability density function. P returns the cumulative density function. Q returns the inverse cumulative density function, meaning the quantiles. R returns randomly generated numbers. As we will soon see, there are 4 functions that can be used to generate the values associated with the normal distribution, namely D norms, P norms, Q norms, and R norms. But let's move on to the next lesson and see how R supports the normal distribution. Data can be spread out in different ways, but there are many cases where the data tends to be around a central value, the mean, with no bias left or right, and it gets close to a normal distribution, also called bell curve. The normal distribution is one of the most used distributions in data science. Many common phenomena that take place in our daily life follow normal distribution, such as the income distribution in the economy, students' average grades, the average height in populations, etc. In addition to this, the sum of small random variables also turns out to usually follow a normal distribution according to the central limit theorem. If we know the values of the distribution mean and the standard deviation, we can then easily find out the probability of predicting exact values by just examining the probability distribution. Since 68% of the data lies within one standard deviation of the mean, 95% within 2 standard deviations of the mean, and 99.7% within 3 standard deviations of the mean. In data science, many machine learning models are designed to work best using data that follow a normal distribution, such as the Gaussian naive Bayes classifier, linear discriminant analysis, quadratic discriminant analysis, and least squares-based regression models. Additionally, it is also possible in some cases to transform not normal data into a normal form by applying transformations such as logarithms and square roots. R offers the following built-in functions that are related to normal distribution. D-norm function. Given a set of values, D-norm returns the height of the probability distribution at each point. If you only give the points, it assumes you want to use a mean of 0 and standard deviation of 1. The general syntax is d norm x, mean equals 0, sd equals 1, log equals false. P norm function. This function gives the probability of a normally distributed random number to be less than the value of a given number. The general syntax is norm q, mean equals 0, sd equals 1, lower dot tail equals true, log dot p equals false. Q norm function. This function takes the probability value and gives a number whose cumulative value matches the probability value. The general syntax is q norm p, mean equals 0, sd equals 1, lower dot tail equals true, log dot p equals false. And R norm function. This function is used to generate random numbers whose distribution is normal. It takes the sample size as input and generates that many random numbers. The general syntax, random and mean equals 0, sd equals 1. In the general syntax of the four normal distribution functions, x and q are vectors of quantiles. P is a vector of probabilities. N is the number of observations if length n greater than 1, the length is taken to be the number required. Mean is the vector of means and SD is the vector of standard deviations. Parameters log and log.p are logical type if true. Probabilities p are given as log p. Parameter lower dot tail is also logical if true default. And probabilities are px equals x otherwise, px greater than x. For example, p norm 0 equals 0.5 and this is the area under the standard normal curve to the left of 0. Q norm 0.9 equals 1.28 and 1.28 is the 90th percentile of the standard normal distribution. R norm 100 generates 100 random deviates from a standard normal distribution. In addition, each probability function has parameters specific to that distribution. For example, random 100, m equals 50, sd equals 10 generates 100 random deviates from a normal distribution with mean 50 and standard deviation 10. If we assume that the test scores of a college entrance exam fits a normal distribution, that the mean test score is 72, and the standard deviation is 15.2, then what is the percentage of students scoring 84 or more in the exam? Questions like this can be answered in R using the built-in p-norm function of a normal distribution with mean 72 and standard deviation 15.2. Since we are looking for the percentage of students scoring higher than 84, we are interested in the upper tail of the normal distribution, so we form the following statement in R. P-norm 84, mean equals 72, SD equals 15.2, lower dot tail equals false. The result returned is 0.21492. Thus, the percentage of students scoring 84 or more in the college entrance exam is 21.5%. In these screenshots you can see examples of applying normal distribution functions in R, along with some simple graphs that illustrate the results. On the left example we first create a vector with the sequence of numbers from -20 to 20 and a STRP of 0.1 then. We use this vector as argument in function dnorm and we plot both the initial vector and the produced values. In the second example, we start with the same vector but pass it as an argument to the pnorm function along with mean equals 5.0 and SD equals 1.0 and we plot the initial vector and the produced values. In the example on the left we first create a vector with the sequence of numbers from 0 to 1 and a step of 0.05. Then, we use this vector as argument in function qnorm and we plot both the initial vector and the produced values. In the second example, we create the vector that is assigned the output of our norm with 50 as argument. Then, we produce a histogram with the results. The binomial distribution is a discrete probability distribution. It describes the outcome of n independent trials in an experiment. Each trial is assumed to have only two outcomes, either success or failure. For example, tossing of a coin always gives a head or a tail. The probability of finding exactly 3 heads in tossing the coin repeatedly for 10 times is estimated during the binomial distribution. In the general syntax of these functions, x is a vector of numbers, p is a vector of probabilities, n is number of observations, size is the number of trials, and prob is the probability of success of each trial. R has 4 inbuilt functions to generate binomial distribution. dbinom x, size, prob, gives the probability density distribution at each point. pbinom x, size, prob, gives the cumulative probability of an event. It is a single value representing the probability. qbinom p, size, prob, takes the probability value and gives a number whose cumulative value matches the probability value. rbinom n, size, prob, generates required number of random values of given probability from a given sample. For example, let's suppose there are 12 multiple choice questions in a quiz. Each question has 5 possible answers, and only one of them is correct. We want to calculate the probability of having 4 or less correct answers if a student attempts to answer every question at random. Since only 1 out of 5 possible answers is correct, the probability of answering the question correctly is 1/5 equals 0.2. We can find the probability of having exactly 4 correct answers by random attempts in R with the following statement. dbinom for size equals 12, prob equals 0.2. This statement will output 0.1329. To find the probability of having 4 or less correct answers by random attempts, we apply successively the function dbinom with x equals 0.4. A faster way to do it is by using the cumulative probability function for binomial distribution pbinom. Both ways are illustrated in the screenshot. The probability of 4 or less questions answered correctly by random in a 12-question multiple-choice quiz is 92.7%. In this screenshot you can see examples of the other 3 binomial distribution functions supported in R. We first use the pbinom function to calculate the probability that we will get 23 or less coin heads after 58 tosses. Then we use the qbinom function to calculate how many heads we will get if we assume that the probability is 0.25 and we toss the coin 58 times. Last, we use the rbinom function to calculate 6 random values from a sample of 300 values with probability 0.3. The chi-square distribution with k degrees of freedom is the distribution of a sum of the squares of k independent standard normal random variables. The chi-square distribution is a special case of the gamma distribution and is one of the most widely used probability distributions in inferential statistics, notably in hypothesis testing and in construction of confidence intervals. The chi-square distribution in the form of the chi-square test, which is based on it, allows us to determine if 2 categorical variables have a significant correlation between them. Both those variables should be from the same population and they should be categorical yes/no, male/female, red/green/blue, etc., and not numerical. In the chi-square test, we have to check the p-values, and like all statistical tests, we assume this test as a null hypothesis and an alternate hypothesis. The main thing is, we reject the null hypothesis if the p-value that comes out in the result is less than a predetermined significance level, which is 0.05 usually. Then we reject the null hypothesis. Remember that the null hypothesis is that the 2 variables are independent. Let's suppose that we have counted for each person buying muffins from our store the kind of muffin they preferred and the gender of each person. Using the chi-square distribution we can decide if there is a correlation between the gender of a person and the flavor of the muffin. If a correlation is found, we can plan for appropriate stock of flavors provided that we have some idea of how many male and female customers we will serve. To perform the chi-square test in R, we use the function chsq.test and pass the data as an argument. Data must be in form of a table containing the count variable values observed. In the example below we apply the chi-square test to a data matrix concerning owner gender and pet, either cat or dog, and examine if there is a statistical correlation between the 2 variables, meaning gender, per preference. Since we get a p-value less than the significance level of 0.05, we reject the null hypothesis and conclude that the two variables are in fact dependent. R offers a set of 4 built-in functions for the chi-square distribution. These functions work just like the functions for the normal distribution. The first difference is that it is assumed that you have normalized the value so no mean can be specified. The other difference is that you have to specify the number of degrees of freedom. The commands follow the same kind of naming convention, and the names of the commands are dchipsq, pchipsq, qchipsq and rchipsq. Arguments x, q are vector of quantiles, p is a vector of probabilities. N is the number of observations. Df is the degrees of freedom non-negative, but can be non-integer. NCP is the non-centrality parameter non-negative. Log.p are logical if true. Probabilities p are given as log p. Lower dot tail is logical if true default. And probabilities are px equals x, otherwise, px greater than x. In the examples from RStudio that follow, you can see how these four functions can be used. On the left, we see how to call the dchipsq function with 7 degrees of freedom to a vector with numbers from -10 to 10 with a step of 0.5. On the right we see examples of applying the pchipsq function to calculate the cumulative probability for values in a vector and 7 degrees of freedom. Then we use the qchipsq function to calculate the inverse cumulative probability for values in a vector and 253 degrees of freedom. Last, we use the rchipsq function to generate 3 random numbers that follow the chi-square distribution with 20 degrees of freedom. Poisson distributions are very useful where we are trying to count events over a period of time given the continuous rate of events occurring, such as the number of patients entering a hospital's emergency department in 3 hours. Therefore, we can think of this type of distribution as the probability of the number of times an event is likely to occur within a certain time frame. Another case these distributions are frequently used is by insurance companies to conduct risk analysis, for example, to predict the number of car crash accidents within a predefined time span and decide car insurance pricing. When working with Poisson distributions, we can be confident of the average time between the occurrence of different events, but the precise moment an event might take place is randomly spaced in time. In R we can draw n values from a Poisson distribution with a mean determined by the argument lambda. For example, we can execute R Poisson equals 100, lambda equals 3. R also provides the additional built-in functions dpoise, ppoise, and qpoise. In the arguments of the full syntax, lambda is a vector of non-negative means. The exponential distribution is used for modeling scenarios like the time you need to wait before your bus arrives, knowing that there is a bus every 15 minutes. The exponential distribution should come to mind when thinking of time until event, or time until failure. Another common application of exponential distributions is survival analysis, e.g. expected life of a device/machine. In R we can sample n values from an exponential distribution with a given rate. Default is 1 using the rexp function with argument n equals 100 and rate equals 1. R also provides the additional built-in functions dexp, pexp, and qexp. The uniform distribution refers to a probability distribution for which all of the values that a random variable can take on occur with equal probabilities. Consider the toss of a single die. The outcome of this toss is a random variable that can take on any of 6 possible values, 1, 2, 3, 4, 5, or 6. Each of these outcomes is equally likely to occur. The probability that any particular outcome will occur is equal to 1/6. Therefore, the outcome from the toss of a single die has a uniform distribution. In R we can sample n values from a uniform distribution also known as a rectangular distribution between 2 values. Defaults are 0 and 1 using the runneth function. For example, we can execute runneth n equals 100, minimum equals 0, max equals 1, where minimum and max are the lower and upper limits of the distribution and must be finite. R also provides the additional built-in functions dunif, punif, and qunif. In this video we discussed how R supports a variety of built-in functions for calculations of statistical distributions. More specifically, we talked about the normal distribution and the four functions R offers. We discussed the binomial and the chi-square distribution functions. In addition, we also presented functions for the Poisson, the exponential and the uniform distributions and gave some examples of their usage.